Hey guys, shouts out to all of you AP Calc, AB, and BC students that are cramming to study for this AP exam that will be tomorrow. I wanted to record a couple of more examples. There are students that reached out to me that were wanting just a couple more examples for their cramming session, if you will, because they've already done all the practice problems that we put out there. So I have a couple that I'm going to be recording, and let's look at this first one. Okay, so AB1, this is another example that is different from the ones that you've seen from before, okay? So first of all, it says that we are given the graph of f prime of x, okay? The derivative of the continuous function f is given above. Between -5 all the way to 4, it consists of 4 linear pieces in a quarter circle. And you see that the center, I've already labeled it, is at 2, 2. And then for a domain that is x is greater than or equal to 4, it has this established f prime of x function that is -2e to the 4 minus x. Finally, we are given an initial value on f, which we don't see f. Remember, we are given f prime, but f of 0 is equal to 6. Okay, so now, immediately I'm looking at f prime is given, and I'm given an initial value of f. So chances are I'm going to be using first fundamental theorem, okay? So I'm going to set up an integral that is relating both levels of functions. I'm going to go from 0 all the way to 4 because I'm trying to find f of 4. So let's say from 0 to 4 of f prime of x in respect to x is equal to change of position of f of 4 minus f of 0. Now, we know f of 0. F of 0 is 6. That was given to us already. So I'm just going to go ahead and put 6. Our goal is to find f of 4 all by itself. So we're going to end up moving this to the left side of the equal sign and making it a positive 6. Okay, so when we added it to the left side, it was plus 6, and there was an already understood positive coefficient in front of this integral right here. So let's go to the graph, and we're going to look for the area underneath the curve between the f prime of x graph and the x axis between 0 and 4. So between 0 and 4, we're looking for this area right here, and we're looking for this area right here. That will give us our displacement, which is this value that's in the box right here, okay? So let's first look at from 0 to 2, okay? We have a square, if you will, from 0 to 2, which is the big square. And it's like the square minus the quarter circle, if you will. That will give us that area that is small, that looks like the small little piece that I shaded in red. Okay, so the square, that's going to be 2 by 2, which is 4, minus that area of that quarter circle. Okay, so it's pi r squared over 4 because it's a quarter of a circle. And we know that the radius is 2 because it's centered at 2, 2. So that's going to be 4 minus pi is this quarter circle. Okay, or sorry, this pi is the quarter circle, and 4 minus pi is the area underneath the graph between 0 and 2. Okay, so we'll say 4 minus pi is this area right here highlighted in green. Okay, so now we're going to go from 2 to 4, which we have a triangle below the x-axis, so it's going to be a negative value, but it's 1/2 times the base of 2 times the height of 2. So we're looking at, this is going to be 2, but a -2 because it's below the x-axis, and we're integrating left to right. Okay, so it's exactly what you see. Be careful with the negative mistakes. So this is going to be a -2 that we're going to be adding as far as from this 0 to 4. So if I have a -2, let me go ahead and put that over here. I'm adding these two pieces together that show that this displacement is going to be a +2 minus pi. And then we can't forget the 6 that we're adding up front, so that we get f of 4 as a total value. Let me go ahead and write it here, is 8 minus pi. All right, so now let's go to part B. Part B is saying find any x values where the graph of f has a point of inflection. So immediately I'm thinking, since I'm looking for a point of inflection on f, I'm analyzing f double prime changing signs, okay? Now, I don't have an f double prime graph, okay? So let me erase a little bit that I did from before. I don't have an f double prime graph. I have an f prime graph, okay? So there's another way that I can interpret this, because if I know that f double prime changes signs, there's two ways that I can change signs. I can say f double prime is changing from a positive to a negative or a negative to a positive. Now, this is equivalent to saying one level up, if you will, f prime of x is changing. I'm going to put it with its respective piece, increasing, which is positive on f double prime, to decreasing, which is negative on f double prime, or decreasing to increasing. Okay, so now if I'm looking at this, I'm going to analyze with this justification right here to explain my reasoning, because I'm looking at an f prime of x graph. So I just have to see, when does it change from increasing to decreasing, or vice versa. Okay, so that's going to change here, here, and we're looking for this entire equation here as well. So we're going to say that the x values are going to occur, so I'll say POIs occur at x is equal to, we're going to say -1, 0, and 4, because that's where f prime changes from increasing to decreasing, vice versa, decreasing to increasing. Again, remember, this is the same as saying that the f double prime changes signs from positive to negative or negative to positive. But I just chose to write it like this because I was given f prime. Remember, use all that you're given in its best context, okay? So let's go ahead and erase that. Let's go to part C. So part C shows or asks, find the maximum. Again, this isn't local or relative, so we're going to go straight to the absolute, which I will go ahead and refer to the candidates test. The absolute value, and when I'm saying the value, I'm not saying where, I'm saying what. What is that value? So I'm looking for the y value, okay, of f of x on the closed interval from -1 to 4. So we're only looking at from -1 to 4. So we're not looking at the entire domains that I had highlighted originally. We're looking at only from, for this particular piece, from -1 to 4. All right. So if I'm looking for the maximum value, and I'm going to use candidates test, I know I already have two candidates ready to be used. Okay, those are the endpoints, -1 and 4. Now, I need to find f of x's critical points, and f of x's critical points will occur at its derivative when it's equal to 0 or undefined. Well, luckily, I have an f prime of x function up here. So I just need to see from -1 to 4, when is this graph going to be equal to 0 or undefined? Well, I know it's equal to 0 at 2. I know it's equal to 0 at -1, but because I already have a -1, I'm not going to relist it. I'm just going to do the 2. Now you're probably asking, wait a minute, isn't there a cusp here at 4? Well, we already have 4. And then you're probably saying, well, isn't there a cusp at x is equal to 0? But here's the thing, f double prime would be undefined. Okay, so f double prime at 0, that is undefined. But that doesn't mean that f prime is undefined, because f prime at 0 is 2. Okay, so with that being said, if it was undefined, it would be like a hole in the graph the way it's written here, similar to that moment at x is equal to -3. Okay, so please make sure that you're not misinterpreting it and seeing that the cusp, and you're going to say f prime is undefined, because that's not the case. It's not undefined here, because we know that y value at f prime of 0 is 2. It's undefined at, if you're evaluating it as f double prime at 0. Okay, so from all that, all we know is that we have this 2 is equal to 0, and there's nothing else as far as a critical point that will be listed as a candidate. So we're going to look for the y value at -1, at 2, and at 4. Okay, so we're going to refer back to this fundamental theorem, because we're going to use our initial value, and we're going to be able to find the y values of these. So let's go ahead and do -1 to what we know is 0. And notice how I set it low to high still. Okay, so f prime of x, in respect to x, is equal to the change in position between f of 0 minus f of -1. Now, our goal is to find f of -1. It's right there. Okay, We know f of 0 was given to us as 6. So I'm going to go ahead and replace this as 6. So whatever algebra you want to do to get a positive f of negative 1 by itself, I'm going to go ahead and move it to the left and say f of negative 1 is equal to, and then move this to the right, 6 minus the integral from negative 1 to 0 underneath the graph of f prime in respect to x. Okay, so now let's find this area. Let me highlight it in purple between negative 1 and 0 in the x-axis. Okay, so negative 1 to 0 is going to be right here. Let me highlight it in purple. And this is a triangle that has a base of 1, a height of 2. So 1/2 times base times height. And it's above the x-axis, so this is going to be a positive 1. Okay, so this is a positive 1 value. So 6 minus 1, your y value is going to be a 5. Okay, now if I want to find the y value of 2, I'm going to set up the integral the same-ish. I'm going to have low to high. Watch how I do this differently for 2. I'm going to say from the established x value of 0 to this x value of 2, it will be then, first fundamental theorem-wise, f of 2 minus f of 0. Well, again, I already know f of 0 is 6. So I'm going to go ahead and plug in 6 right here. And now when I add it to the other side, I'm going to have f of 2 all by itself. So 6 plus whatever this is, when I move it to the other side, I'll get f of 2, okay? So now in blue, we're going to highlight the area underneath the curve between 0 and 2. Okay, so in blue, let's go ahead and highlight the area underneath the curve between 0 and 2. Okay, so this we already found from part A. Now it's not the full 8 minus pi, but this came from that square that was 2 by 2 minus that quarter circle, which is pi r squared over 4. We know that the radius was 2, so this became 4 minus pi. So 4 minus pi is going to be that value here, but then we have to add this 6 to it to give me 4 minus pi plus 6 is going to be 10 minus pi for the value of 2. Okay? And last but not least, let's go ahead and set it up. We're going to set up this first fundamental theorem. Let me rewrite that. And this time we're going to go from 0. And I would recommend using the point that they give you. If not, you can go from points that you get so that you can do less area, if you will, and kind of go from where you left off, which I'm actually going to do that. I'm going to go ahead and do that. But you have to trust your answer, okay? You got to make sure that this is correct. Otherwise, you might start off incorrect as far as your answer goes, okay? So we're going to go to set 2 to 4. Therefore, f of 4, first fundamental theorem wise, minus f of 2. And remember, we're trying to find what is f of 4 right here. Okay, so f of 4. What is the y value when x is 4? That's what we're looking for. So we know from the previous piece that f of 2 is 10 minus pi. So I'm going to add it to the left side. So you have 10 minus pi, which is adding to this left side. There's a positive coefficient there. And since I added it, there's a positive coefficient there. Now you know that I don't need those pieces, so I'm going to go ahead and erase those. And then we'll see what is the area underneath the curve in green right here between 2 and 4. So between 2 and 4, we have this, again, 1/2 times base times height. We've already done this, but it's a negative interpretation. It's going to be a negative 2. So that area underneath the curve from 2 to 4 is a negative 2, which we will add with 10. 10 plus a negative 2 is an 8, so it would become 8 minus pi. Okay, so now I just have to look at these y values, and by themselves, as they sit, these y values right here, which one is the absolute maximum? Which one's the highest or the biggest value, if you will? Okay, so obviously the answer is going to be 10 minus pi. Okay, so you're going to say the max equals 10 minus pi at x is equal to 2. Now, I know it didn't ask you to put the at value, but if you want to overkill it just a little bit and make sure that you get all the points that you need, make sure that you do, in fact, write it out and list not only your work, but also refer to per candidate's test. A big also pointer that a lot of students forget to at times to mention is What derivatives are you setting equal to 0? How are you analyzing critical points? And what functions do they refer to? So make sure you put all that intermittent work, because that's what the AP readers are looking for. All right, let's go to part D. It says write an expression for g prime of x and g double prime. Well, they gave us this function right here. G of x is this function right here. So already it's screaming at you second fundamental theorem. Okay, so if I want to take the derivative of the left side, well, that's easy. It's just g prime, which is what we're looking for here. So the derivative of the right side, remember, it is basically going to do the carbon copy of what you see, and then you're going to go ahead and plug in those limits of integration and so on and so forth. Okay, so first of all, the derivative of 3, this is going to zero out. It's gone. When you take the derivative of any constant, you know already that it's going to zero out. So on the left side, we'll have g prime of x. And on the right side, this is how I showed my students. When you're taking the derivative of an integral, we know it's second fundamental theorem. So we're going to take the integrand, that entire piece in the integral symbol, and we're going to make a carbon copy and call it f of b. Okay, so it's like 2f prime 2 parentheses. Again, we're going to put parentheses where we normally would have seen a t, or whatever that input variable is right there that we're in respect to. And then we're going to subtract. Oops, I forgot to copy over. That's very, very, very important. I have to copy the entire integrand. And then we will subtract the entire integrand. And again, the only place that I'm going to replace with the parentheses is where the t used to be. Okay, so the t used to be where 2 is at, right next to it. So that's parentheses. This is the shortcut for doing f, or second fundamental theorem, f of b minus f of a. So now, let me highlight it as I go. I'm going to plug in an x right here where the variable of t used to be. And then I'm going to multiply this entire piece by the derivative of said x value. Okay, so the derivative of x in respect to x is just 1. Okay, now over here, let me highlight it in purple. I'm going to plug in a negative 1 where the t used to be. And then I'm going to multiply, because it's chain rule. What is the derivative of negative 1? Well, that zeroes all of this out, because the derivative of any constant, in this case a negative 1, will zero all of that out. So what I'm left with is just this piece right here. Okay, so I'm going to go ahead and rewrite this as my g prime a little cleaner. And I'm going to say 2f prime of 2x plus 1. This is my g prime of x. Okay, so now I'm going to go ahead and just take the second derivative from here. I don't even have to look at my original equation, because I'm just going to take it from where it's at right now. And I can see right here there is going to be a chain rule piece. So let's take the derivative. That's f double prime of this stuff multiplied by the derivative of that inside piece. Well, that's 2. And then don't forget this constant multiple rule that you have to multiply. That 2 is out there just waiting to multiply with whatever you get from that derivative piece of f prime of 2x. Now the 1 will zero out. It's gone. Okay. Now one thing that I just realized is that when I did this integral, okay, one thing that I forgot that's very important. A lot of you probably like, whoa, wait a minute. What happened to this negative? This negative is going to distribute on my answer. So this actually makes this a negative. There's some negative mistakes. Be careful with those. We all make them though. I caught myself there. It's going to be a negative 2 times f prime of 2x plus 1. Okay, that means that's negative is in parentheses. So you could write it like this. Or if you wanted to write it like negative 2 f prime of 2x, then you would distribute that negative. You could write minus 1. Okay, so either way, or g prime of x is equal to all of this. Same thing. Okay, I'm going to go ahead and keep it as this one for now. And I'm going to make sure that I have these brackets right here. Okay. So now when I take the derivative, the only thing that I was missing was this negative 4, if you will. So I need to make sure that I have this negative 4 piece included as well, okay? So let me go ahead and write that out. Let me put a negative, and then I will put a 4 to clean it up some. So negative 4 times f double prime of 2x. Remember that 1 zeroes out, it's gone. And then I'm left with these. So let me clean this up one more time, because I don't want you to be confused as far as what I have here. So -2, and then parentheses, all of that. Or again, if you wanted to, and I'm just realizing something, struggling just a little bit right now, -2 would go here as well. So either that or the one that I have here with the bracket. So I'm going to go ahead and stay with the bracket. Okay. So -4 is still becoming f prime of 2x. Oh, and then f double prime. I erased it on accident. I need to write it in. So this is my second derivative. Now we can keep going. So part E, it says, does the graph of G have a local maximum, minimum, or neither at x is equal to 2? Guys, guess what? We finally, it's been a while, we get to use second fundamental theorem. Otherwise, if you're looking at f prime and you try to include test points, this one actually is a little bit more difficult of you trying to use the f prime of x with the first derivative test than if you just go straight to the second derivative test. Again, repeating, first and second derivative tests are aiming to find relative max or mins. That's it. Nothing else. That's it. That's what you use these for. We already know that the first derivative test will find a max when f prime of x changes from positive to negative. We know that the f of x will have a relative min when f prime of x changes from negative to positive. But we forget sometimes how to use this second derivative test. Okay, the first stipulation for the second derivative is that the first derivative, which in this case, the at value is 2, must equal 0. Okay, and imagine that's like a horizontal tangent at 2, anywhere. Could be up here that the horizontal tangent is 0. Now, f double prime at 2, if it is positive, that means it's going to be concave up. There's a relative min right there. If f double prime was negative, well, then it will be concave down, and there's going to be a relative max there. So a quick review on that. Those are the two stipulations that you're trying to find, is what is the sign at the second derivative? And does, in fact, at the first derivative, do I have a horizontal tangent, which is what I need. Remember, I need that local linearity piece that shows I have a horizontal tangent at that particular x value. Okay, again, that is second derivative test. Okay, you might have to go in your notes, kind of refine with that, possibly, but that's how we're going to use it. Okay, so let's look at f prime, sorry, not f prime. In this case, we're looking at G has a local max or min, max, or neither at 2. So we're going to evaluate what is G prime at 2. Okay, so G prime of 2 is taking this equation here, plugging a 2 in, so that I'm really looking at -2 times this f prime at 4 plus 1. Okay, so what's f prime at 4? Well, f prime at 4 is -2. Because remember, this is an f prime graph, not an f of x graph. Okay, so it's the y value at 4. So this is going to be a -2 plus 1, which is a -1. And when we multiply that with the -2, we get what? -1 times -2 is a +2. We don't get the 0 that we need in order to use second derivative test. Okay, so this is going to be neither. And you could say it fails the second derivative test, or you could just say G prime of 2 is not equal to 0. So remember, it has to have these, it has to have both of these conditions, right? And then analyzing whether that second derivative was positive or negative to see if it was concave up or down and go from there. Because it doesn't even have the first stipulation, then it's neither. It's not going to be a local max or a local min per second derivative test. Let's go ahead and finish off with F now. It says, does the graph of G have a point of inflection at 2? Point of inflections, we know, for definition of point of inflection, that we are looking specifically for this one at G. So we're going to analyze its second derivative at 2. Kind of looks like we're going to do a little bit what we did in E, but it is going to be a little bit different. Let's first of all find what is G double prime at 2. So G double prime. G double prime at 2 means I'm going to use this equation. So I'm going to have negative 4 F double prime of 2. And again, because we're looking at 2, it's really going to be F double prime at 4. So what's this derivative or F double prime at 4? Well, at 4, because this is F prime, the derivative would be, what's the slope? What's the F double prime at 4 going to equal? Well, this is a cusp. So we know that this is going to be undefined, okay? So the point of inflection will occur not whenever G double prime of 2 is equal to 0 or undefined. That's not, and that's a common mistake a lot of students think. If it's 0 undefined, that's a point of inflection automatically. But that's not how it works, okay? We know that this is undefined. And undefined times negative 4 is still undefined per se, or does not exist, however you want to look at it. But nonetheless, we need to look at sign changes. That's the biggest thing whenever we're looking for a second derivative analyzing its point of inflection. Okay, so we want to know if this was like G double prime, and the moment was at 2, does it have a change of signs from negative to positive or from a positive to a negative? This will tell us if those sign changes occur, then there is a point of inflection at 2, okay? Pending that, in fact, we do have a y value on 2. And we will have a y value on 2 because it says that f, right? Whoops, where is it at? We will have a value of 2 because we have this g of x graph basically showing from this equation here, okay? So we just want to see, are there sign changes that occur around this moment at 2? Okay, so let's go ahead and let's test some out. Okay, we're going to test to the left of 2. Let's try 1. So G double prime at 1, we want to see what is the sign. Well, it's negative 4 times F double prime negative 1. Let me highlight it in purple. We're using this function. We're putting a, not a negative 1, a positive 1 here so that we have F double prime at 2. Okay, so what's F double prime at 2? Well, that 2 is a cusp. Okay, so that's an undefined piece in itself. So this one's a little bit more hefty as far as how are we testing our points, if you will. So let's say I didn't use a 1. Okay, because we're getting the choices that we're making, we're getting these weird cusps answers. So what if I used, instead of 1, what if I used something like 1.5? Okay, so 1.5-ish is what we're looking for. Something just to the left of 2. So that means I would put 1.5 in here, okay? And 1.5 is 3/2, and we multiply that by this 2. Again, we're putting this as far as our x value in our G double prime. So we're looking at F double prime at 3. So at 3, we know that this slope is down 1 over 1, down 1 over 1. F double prime, because this is an F prime, is going to be a negative 1. Not because it's the y value, but because the slope of this line of the given f prime of x graph is a negative 1, okay? So we'll have a negative 1 times this negative 4 is going to be a positive 4, so we know it's positive on the left side of our 2 moment, if you will. Now let's try our last interval. Let's say we chose 3. And we chose 3, and we plugged it into this function, G double prime, then we'd have F double prime of 6. Well, what's the derivative of this function at 6? Well, the derivative is some kind of positive. It looks like maybe up 1 over 2, up 1 over 2. But nonetheless, it's positive because F prime was increasing. Okay? So we know it's a positive of some kind. And a positive multiplied with this negative 4 that I just erased, did not mean to. But this negative 4 right here is going to be a negative. So a positive times a negative is a negative. And sure enough, check that out. We have a sign change going on. So we're going to say, per the definition of point of inflection, yes, the graph G has a POI at x is equal to 2. And you can say, because G double prime of x changes signs. And you could say at 2 or around 2, or you could say changes signs from positive to negative. And that's it. Hope this extra practice helps, guys.